the equation that predicted nothing we could see. It was elegant, internally consistent, and mathematically flawless. Yet when applied to the universe, it pointed towards something that refused to appear. The numbers balanced perfectly. The logic held firm, and still the result described a reality that no telescope, sensor, or instrument could directly observe. To understand why this equation still matters today, we need to return to how theoretical science shapes discovery. Long before instruments confirm what exists, equations often arrive first, translating patterns into predictions that guide where humanity looks next. Modern physics depends on this relationship, trusting that mathematics reveals truths hidden beyond immediate perception, because history has shown that invisible forces often announce themselves through numbers long before they are seen. That trust is what gave this equation its power. Derived to resolve inconsistencies in existing models, it emerged not as speculation, but as necessity, a solution required to keep fundamental laws intact. Without it, the equations governing motion, energy, and structure simply did not work as expected. With it, everything aligned, except for one problem. The solution implied the presence of something vast and influential that no observation could confirm. At first, this absence was treated as a limitation of technology. Scientists assumed the predicted entity was simply too faint, too distant, or too diffuse to detect with current tools. That explanation was comforting, because it preserved confidence in both theory and observation. The universe had hidden something, but not forever. As years passed, instruments improved. Surveys expanded and sensitivity reached levels once thought impossible. Yet the predicted presence remained unseen. The equation continued to work, producing accurate results across countless scenarios, while the thing it described remained stubbornly invisible. What made the situation unsettling was not failure, but consistency. The equation did not break. It succeeded everywhere it was tested, except in revealing what it claimed must exist. The universe behaved as if something unseen was shaping it, bending outcomes without ever stepping into view. Slowly, a realization took hold that the problem might not be observational delay, but perspective. The equation was not predicting an object waiting to be found, but a form of influence that did not behave like anything humanity was accustomed to seeing. In confronting that possibility, science faced a profound question. What happens when mathematics describes reality more completely than observation ever has? As the equation continued to succeed where observation failed, confidence in its implications grew alongside discomfort, because it became clear that dismissing the result would unravel far more than accepting it. Removing the unseen component caused entire models to collapse, producing contradictions that could not be reconciled without abandoning principles that had been verified repeatedly. Researchers tested every alternative. Measurement errors were scrutinized, assumptions were relaxed, and competing formulations were explored in search of a version that could describe the universe without invoking something invisible. Each attempt either failed outright or quietly reintroduced the same missing influence under a different name, reinforcing the idea that the equation was pointing towards something fundamental rather than optional. The difficulty lay in how unfamiliar prediction was. Science had a long history of uncovering hidden entities, but they eventually revealed themselves through interaction, emission, or direct effect. This predicted presence behaved differently. It influenced motion and structure, yet refused to interact in ways that produced light, heat, or any signal that instruments were designed to detect. As observational campaigns expanded, the absence became harder to ignore. Entire regions of space behaved as though shaped by an unseen hand, with galaxies rotating too fast, clusters holding together against expectations, and large-scale structures forming in patterns that defied visible matter alone. The equation explained these outcomes elegantly, while observation remained silent. This imbalance created a philosophical tension. Accepting the equation meant trusting mathematics over direct perception, a reversal of how knowledge is often validated. Rejecting it meant accepting that the universe consistently behaved incorrectly according to known laws. Neither option was comfortable. In that space between certainty and doubt, the equation gained an unsettling authority. It described a universe that worked, even if it could not be seen, forcing humanity to reconsider whether reality is defined by what is observed or by what must exist for observation to make sense at all. The conflict reached its most intense point when the implications of the equation began to outweigh the discomfort of its invisibility, because the alternative was a universe that simply did not add up. Entire frameworks of physics depended on internal consistency, and abandoning the equation meant accepting contradictions that would ripple through everything from planetary motion to the large-scale structure of the cosmos. As debates deepened, the scientific community divided along philosophical lines. Some argued that an unseen influence, no matter how mathematically elegant, remained speculative until directly observed, warning that history was filled with beautiful ideas that ultimately prove wrong. Others countered that observation itself is limited by the tools we build, and that mathematics has repeatedly revealed realities long before instruments were capable of confirming them. What made this conflict especially difficult was how productive the equation was. It did not merely solve one problem, it unified many. Discrepancies that once required separate explanations suddenly aligned under a single framework, suggesting that the unseen component was not an ad hoc solution, but a foundational part of how the universe operates. The more problems it solved, the harder it became to dismiss. Yet acceptance carried its own cost. Embracing an invisible influence meant redefining what counts as evidence, elevating indirect effects and statistical consistency over direct detection. This shift challenged deeply held intuitions about discovery, forcing scientists to admit that some aspects of reality may never present themselves in familiar, observable forms. As the debate continued, the equation became a symbol of a broader struggle within science, the tension between what can be seen and what must be inferred. It asked whether understanding should be limited by perception or expanded through reasoning, even when reasoning leads beyond the reach of sight. In confronting that question, physics found itself standing at the edge of a new kind of understanding, one where absence itself carried weight and invisibility did not imply insignificance. The climax of this story arrived not with discovery, but with acceptance, as the scientific community recognized that the equation described a reality too consistent to ignore, even if it could not yet be seen. The unseen influence became an integral part of models, not because it was proven in isolation, but because without it, the universe refused to behave in coherent ways. This acceptance reshaped how discovery is defined. Physics expanded beyond the expectation that every fundamental component must announce itself through direct interaction, embracing the idea that influence itself can serve as evidence. The equation did not replace observation, but it rebalanced the relationship between seeing and understanding. The resolution did not close the mystery. Instead, it opened new directions of inquiry, inspiring experiments and instruments designed to detect what had once seemed undetectable. The unseen was no longer a failure of perception, but a frontier, one that demanded creativity rather than certainty. For humanity, the lesson extended beyond physics. It challenged the assumption that reality is limited to what fits within existing senses and tools, reminding us that understanding often begins where familiarity ends. The universe does not owe us visibility, only consistency. Today, the equation that predicted nothing we could see remains one of science's most powerful guides, shaping exploration not through what it reveals, but through what it compels us to question. In trusting mathematics to lead where sight cannot, humanity took another step toward a deeper, if more humbling, understanding of the cosmos. Subscribe to join the journey.